Welcome to Data Science with EJD. In this video, we move on to some advanced supervised learning algorithms. And the first we are considering in this case is the idea of ensemble learning. I think when we talked about trying to remember the one, yeah, I think when we talked about uh random forest, I believe. We came up across the idea of bagging, that's boosting aggregation or something like that. So this is coming up again. So under advanced supervised learning, so we have this idea of ensemble learning, to be x-rayed better. So in machine learning, right, ensemble learning aims to improve model performance by combining multiple weak learners, most models slightly better than random chance, to form a strong learner. A very good example of that is the random forest we've been looking at when you combine different trees together, you aggregate them to get a better model, right? So that's one thing, the closest thing to it that we've been seeing so far. So the learning objective, talking about combining weak learners, is this. So the idea is that by leveraging the wisdom of the crowd, the ensemble can outperform any individual model. So if you bring many people together who have different weakness in one area or the other, by the time they contribute all their strengths, you can get something better, right? So core types of ensemble methods include voting, right? That's one method. And the model diversity is very high, it is heterogeneous. The training strategy is parallel. The error reduction, it aggregates strengths. And final prediction rule, majority votes and average probabilities. Then we have bagging. So the model diversity for bagging is low, but it's homogeneous but low, right? The training strategy is parallel. So you are training at the same time, right? And for error reduction, it reduces variance. For final prediction, it takes average and it takes majority for the majority. Then lastly, you have the boosting, which is low in homogeneity, which is homogeneous rather, and it's low. So the training strategy is sequential. So it takes one after the other, and then the error reduction is such that it reduces bias, and it takes the weighted sum of and it takes the weighted sum and it is an additive model. All right. So talking about voting now, which is the first method we'll be looking at for ensemble methods. So voting is aggregating predictions across diverse models. So voting voting combines the predictions. Let me split this up like this. So voting voting combines the predictions of multiple typically diverse models, e.g. logistic regression, decision tree, SVM. So it typically combines the predictions of all this. Then each model contributes to the final decision via a voting mechanism. So it's more like you look at all of them and you pick the very best of them, right? So types of voting, there's hard voting where, okay, do I need to split this? Yeah, let's leave it this way. So there's hard voting where each classifier casts one vote for a predicted class label. So the class with the most votes win. And then there's soft voting where each classifier provides probability estimate for each class. The final prediction is made by averaging these probabilities and selecting the class with the highest mean probability. Okay, so those are the two types of voting: hard voting and soft voting. When do you use voting? You have different types of classifiers trained on the same data. So if you have different types of classifiers trained on the same data, you can use voting. And then you also want to balance out their individual strengths and weaknesses. That's when you use voting. So let's look at an implementation. Okay. Let's show the line numbers for easier referencing. So how do you so you need a voting classifier here, right? We're talking generally about advanced supervised learning. So we can be talking about both classification and regression algorithms. So it's fine. So this is particularly for talking about classifiers, right? So of course you need sklearn from Ensemble. You get voting classifier. You need logistic regression from linear model. Then you have sklearn tree, decision tree classifier, the SVM. You put everything together and then you vote for the best, or whether you go according to whether you're using hard voting or soft voting. All right, for data set you're using iris for this, and then the usual test, train, test. And since this is a classification thing, accuracy score is one of the key things we use here. Of course there are other things like precision, recall, and all of that. All right. So you can load the data set XY, load iris, return XY true, X train. This is where you're splitting. So the test size here is 30, meaning that we are using 70% of the data for training and we're using 30% for testing after it has been trained. Then we want to define the base learner. So CLF1, we have logistic regression with 1000 maximum iteration. CLF2, we have decision tree classifier. And CLF3, we have support vector classifier where the probability is true. Then we have ensemble via soft voting. So we have voting CLF, so voting classifier for the estimators. Now you have LR CLF1, DTS CLF2, SVC CLF3, and voting is soft. So that takes care of the voting. And then you have voting underscore CLF dot fit. So this is where you fit the where you train the model, right? And then you can now predict from the model. So voting underscore CLF dot predict X test, and then it prints voting classifier accuracy. So it tells you about the accuracy. Of course, you can already expect, because the iris data set is a very straightforward data set. You can be sure that the accuracy is going most likely going to be one, as you've seen before, even with. Oh, okay, interesting. This is not one exactly, but it's pretty close. 0.9555. So like 0.96 to two decimal places. So the pros of the voting classifier is that it is easy to implement and interpret, and it works well when base learners are diverse and uncorrelated. The cons, that's the disadvantages, it's less effective if models are highly correlated or individually weak. No internal mechanism for correcting individual model errors. So let's go for bagging. Bagging is short for bootstrap aggregating. Bootstrap aggregating. So here, uh, bagging trains multiple instances. Now, when we say instance in machine learning, we are talking about one row. So you are training different, you are taking row by row and you're training. So bagging trains multiple instances of the same base learner on bootstrap samples, random sampling with replacement, and averages their predictions to reduce variance. So you can already imagine that it is a very tedious process. If one model overfits, combining it with others trained on different data subsets reduce overfitting and noise sensitivity. Okay, so the popular variant is random first, like I said before. So bagging plus random feature selection for decision trees. All right, so and the implementation, you use the bagging classifier. So voting, bagging, and boosting is the last. So here we're talking about bagging. So of course, from the ensemble, scikit-learn ensemble, you get the bagging classifier. Then you use the decision tree classifier. You need accuracy score because it's classification you're doing. Then you have the train test splits. We are still using the iris data set. So again, as usual, you have the features X, that's data.data, Y data.target. Like I said, the data set has been so arranged in such a way that when you call this now, you're talking. So data.data gives you the features, and data.target gives you the target, right? So train test split, which is standard, X train, X test, Y train, Y test equals train test split, X, Y. The test size is 30%. Random state is 42 to be ensured nothing changes no matter how many times you run the code. Then you use estimator instead of base estimator for scikit-learn 1.4. So bagging CLF is now bagging classifier. Estimator decision tree classifier is what you're using. Then N estimator, you have that's number of estimators now. Then you have bootstrap is true, random state is 42 again. Then you can feed the model. So you say bagging CLF here dot fit X train Y train. Then you can predict Y pred is bagging CLF dot predict X test. Then print bagging classifier accuracy. So it gives us the accuracy for the bagging classifier. Talking about ensemble. So here, I mean, the iris data set is pretty straightforward and there are no complexities per se. So you have the bagging classifier giving us a 100% accuracy. It's 1.0. So the process is that it reduces overfitting, it's parallelizable, training is independent, and it is robust to noise. The cons is that it doesn't reduce bias. Using a weak base model will still result in poor performance. It is more computationally intensive than a single model. So you're working with different models and you're then picking a way out. So boosting is the last thing we talk about, which is sequential model correction. So it takes model by model and then it keeps correcting until you get what you want. So boosting builds models sequentially. Each new model focuses on an example that previous models got wrong, right? So the final prediction is a weighted combination of all models. So the intuition is that boosting learns from mistakes. So that would seem to be a very good a very good way to go, right? But talking about boosting, early models make errors, later ones specialize in correcting them, which is cool, right? Then popular algorithms for boosting, we have ADA boost. This adjusts sample weights Then you have gradient boost, which optimizes an additive loss function. You have XG boost, light GBM, cat boost, which are scalable, regularized, and high performing variants. Interestingly, I think in the next video, we'll be looking at XG boost and light GBM, right? Um, so for the implementation, we have taken the ADA boost classifier, which operates by adjusting sample weights. So uh, from scikit-learn.ensemble gets ADA boost classifier. Then we use the normal decision tree classifier as the base model, I believe. Then you get the accuracy scale to say what the performance looks like. So it creates ADA boost classifier with decision stump as a base estimator. So you have ADA boost CLF, ADA boost classifier. Estimator is decision tree. Maximum depth is 1. Number of estimators and yeah, is 50. Learning rate is 1.0. Algorithm is SAMME. Use SAMME to avoid deprecation warning. And then random is deprecation is all about something that used to work in a version of Python not working anymore in an upgraded version, right? So if you want to avoid a warning about this, you just use this. If you don't use it, so it's still fine, because but the warning just tells you that that's no, whatever it's warning you about is no longer in use. So you can now feed the model to the training data. So you have adabus underscore clf dot fit x train comma y train. Then you have predict on the test data y predict adabus underscore clf dot predict x test. So then you evaluate and print accuracy, right? So you evaluate and print accuracy. So print other booster classifier accuracy. So you have accuracy underscore score y test y pred, and then that gives you an accuracy of 1.0. So that's perfect, right? And that's likely because the iris dataset is a very straightforward dataset. So you don't want to forget that. So the pros are it reduces both bias and variance, and it works well with weak learners, e.g. shallow trees. Then it often achieves state-of-the-art performance, like we see 100% performance on this data set. So it is sensitive to noise and outliers. It is harder to parallelize because you have sequential dependency, and there's risk of overfitting if not tuned properly. I think in the future we're talking about hyperparameter tuning and things like that, right? So these are the disadvantages of boosting like that. So let's look at the comparison summary. So for feature, we have the base learners for voting, they are heterogeneous. For bagging, they are homogeneous. For boosting, they are homogeneous. For training type, parallel, sequential. Main focus, voting focuses on model diversity. Bagging focuses on variance reduction. And boosting focuses on bias reduction, right? Overfitting risk is low for voting if diverse. Bagging, it's low also. For boosting, it is medium to high. Overfitting, so you can easily have overfitting risk with boosting. Interpretability, for voting, there's high interpretability. Bagging is medium and boosting is lower because it's the process is a bit more complex than the rest. Example library, you have the voting classifier, bagging classifier, other boost classifier, which we've used up there to get these results. So use cases and when to use what. When do you use what? So first of all, if you have different types of models and want to combine them, you use voting. If your base model has high variance, e.g. decision tree, which has high variance, you use bagging. You need high accuracy and can handle training complexity, you need boosting. If you need interpretability, if interpretability matters and models are already strong, you use voting. If data is noisy and you're worried about overfitting, bagging is what you need. If you want to squeeze the most predictive power from weak learners, boosting is where you go. All right. So in final thoughts now, ensemble methods are cornerstones of modern machine learning and are widely used in competitive data science, e.g., Kaggle and production systems. The choice between voting, bagging, and boosting depends on your data's nature, the individual model strengths, the trade-off between performance, interpretability, and computational cost. So, voting classifier offers a simple yet effective way to combine diverse models, serving as a great starting point for ensemble learning. So, if you're starting out with ensemble, voting classifiers will do the job. So, feel free make it avail yourself of this knowledge and go ahead and use ensemble methods if you have many weak learners that you're working with. All right, so this brings us to the end of this particular video. Let me know how helpful this is to you, and if there's something you'd like me to try out, feel free to let me know also. If you have subscribed to the channel, thank you. If you haven't subscribed, please go ahead and subscribe, and be sure to hit the notification bell so you can always get alerted each time a new video is released. Okay, And now on my channel, there's membership. You are free to join as a member with some extra privileges, like having a badge displayed around your name. With respect to my channel, you can also have access to my math PDF notes on request, and we can also have like consultancy depending on based on whatever I do on this channel. So you definitely want to be part of that. As much as possible. And if not, if you're just a subscriber, you're good. You have access to most of the videos I have going on here. Be sure to like and share for sure so that more people can have access to these things. Till I come your way again, keep doing data right. Bye.